Hello friends, welcome to HU Diamond Academy. In the last lecture we were discussing about the groups of unity. Okay, so in this particular lecture we will discuss about the theorems on the cyclic group. So what we have seen in the concept of cyclic group is that suppose there is an element A that is existing in G, then we have, if this element is generating the whole group, then we call that group as a cyclic group, and this element that is generating the whole group is called generator. So the representation is, this is generating the whole group, this is equal to G. Suppose B is generating the whole group, then we have the structure as this one. Okay, so we have the basic structure for the cyclic group is that G is equal to a to the power n such that n belongs to Z plus. Okay, so the elements are in this particular fashion. So this is A, this is A1, A square, a to the power n. A to the power n means the operation. So we have the algebraic structure as G star. Okay, so and G is a cyclic group under operation star. So a to the power n means the operation is applied n times. A star, this is n times. Suppose this is a square, so this is a square is equal to operation is applied 2 times. Okay, so this is our a square is like this. So a to the power cube is operation is 3 times a to the power cube. Okay, so this is the basic concept of the cyclic group. So let us move further. Before proceeding further, let us revise the concept of order of group and order of element. Order of group is equal to number of elements in that group. Okay, so order of group is equal to number of elements in that group. Okay, so let us take example. So we have the set of integers under addition forms a group. Okay, so the elements in Z are infinite elements are there. So we have this as -3, -2, -1, 0, 1, 2, 3. Okay, so these are infinite elements. So order of Z will be order of group Z will be infinity, because there are infinite elements, because the order of group is equal to order of elements in that group. Okay, so now let us take one more example. So we have Z4 under addition modulo 4 forms a group. What will be the order of Z4? So elements in Z4 will be, this is 0, 1, 2 and 3. Okay, so this is 0 to n minus 1, that is 0 to 4 minus 1. So elements will be 0, 1, 2, 3. The number of elements in Z4 will be, so order of Z4 will be number of elements in Z4. So number of elements are 4. So order of Z4 will be 4. Okay, so the order of group is equal to number of elements in that group. Okay, now let us discuss order of an element. Okay, so now let us discuss about the concept of order of element. Order of element in a group. So let G be a group under operation star. Okay, now since G is a group, there must be an identity element. So let us take G as, there must be identity element. Let us take the elements as A, B, C like this. Okay, so let us find order of A. Let us take element A. Okay, so as per the definition of order of A, if P is the order of P is the order of element A, then A to the power P is equal to identity element. Secondly, P must be smallest natural number. Okay, so if P is the order, then A to the power P is equal to identity and P must be the smallest natural number. Suppose A to the power square is equal to identity and A to the power 4 is also identity, then the order will be 2. Order of element A will be 2. So this is represented as order of element A is equal to 2. Okay, Find the order of A. This is represented as like this. So order of A is equal to 2 because 2 is the smallest natural number. Okay, because a to the power square is also E and a to the power 4 is also E. Okay, both are resulting into identity element. Okay, so this is a to the power p is nothing but p times operation on element A. So this is a star, a star, a star, like this. This is applied p times. Okay, so this is the concept of order of an element. Okay, so let us discuss this with an example. So we have, let us take an example, Z4. This forms a group under addition modulo 4. Okay, so the elements in Z4 are, this is 0, 1, 2, 3. Okay, so let us find the order of element 2. Okay, so let us find order of element 2. Okay, or this is represented as this one. Okay, let us apply the operation on this element 2. Okay, so we have the algebraic structure as Z4 and the operation is addition modulo 4. Okay, so we have 2 to the power 1 one time operation. This is 2 mod 4. This is equal to 2. Okay, 2 to the power square matlab 2 times operation. So this is 2 plus addition modulo 4 into 2. So this is 4 mod 4. The remainder is 0. Okay, now we have 2 to the power 3. So this is 2 plus addition modulo 4. This is 2 square. So this is 2 plus addition modulo 4 and 2 square is 0. So this is 2 mod 4. So the remainder is 2. Now we have 2 to the power 4. This is 2 plus addition modulo 4 and this is 2 to the power 3. So this is 2 plus addition modulo 4 and 2 to the power 3 is 2. So this is 4 mod 4. So this is 0. So elements are getting repeated. Okay. So we have, as per the definition of element, order of an element in a group, we have the condition as, the first one is a to the power p is equal to identity element, and secondly p must be smallest natural number. So let us identify here. So we have in Z4, in this group we have the identity as 0. 0 is the identity. So here 2 to the power square is equal to 0, that is identity, and 2 to the power 4 is also 0. So we have to take the smallest natural number. So here the order of 2 is equal to 2. Okay, because we have to take the smallest natural number. Okay, because 2 to the power square is giving identity. Okay, 2 times operation addition modulo 4 on this 2 is giving identity element. Okay, so we have the order of element 2 as 2. Okay, now let us find the order of element 3. Find order of element 3. Let us apply the operation here. So we have, let us apply operation one time. So this is 3 mod 4. This is 3 to the power square. This is equal to 3 plus addition modulo 4 3. This is 6 mod 4. 6 mod 4. This is, the remainder will be 2. And we have 3 to the power cube. This is 3 plus 4. This is 3 square. This is 3 plus 4 and this is 2. This is 5 mod 4. This means remainder is 1. Okay, 3 to the power 4. So this is equal to 3 plus 4 and this is 3 to the power cube. So this is 3 plus 4 and this is 1. This is 4 mod 4. This is equal to 0. So this means 3 to the power 4 is equal to 0 is equal to identity element here. So order of 3 will be 4. So order of element 3 is equal to 4. So order of element 3 is 4. Okay, so now let us relate this. Order of a cyclic group is equal to order of the generator. Okay, so the order of this cyclic group, that is Z4, is equal to number of elements in Z4. So this is equal to 4 and this is equal to order of its generator. Okay, so the generators here are so we have, let us revise our concept of finding the generator. Okay, what we have seen, so we have ZP forms a group under addition modulo P. Okay, so we have seen that there are two cases. If P is equal to prime and P is equal to not prime. So if P is equal to prime, suppose we have, let us take an example, Z5 under addition modulo 5, and P is equal to not prime, let us take example as Z4 under addition modulo 4. Okay, so if P is equal to prime, then we have P minus 1 generator. So if have ZP is equal to 0, 1, 2 up to P minus 1. So everything except 2, everything except 0 are the generator. So we have the generator as 1, 2 is also a generator, and P minus 1 is also generator. So all these generators are generating the ZP. But in case of this case where P is not prime, if A is the generator, if A is the generator, then we have GCD of A comma P is equal to 1. Okay, so suppose we have Z4 as Z4 is equal to 0, 1, 2, 3. So GCD of A comma 4 is equal to 1. So here A will be 1 and 3. So the generator are 1 and generator are 3. Okay, so in this particular case Z4, the generator of Z4 are 1 and 3. This is equal to Z4. Okay, so the order of group is equal to order of generator. So order of generator is equal to order of generator. Okay, so order of element 1 and order of element 3. Okay, so the order of cyclic group is equal to order of its generator. Okay, so what we have find the order of element 3, this is equal to 4. Similarly, if we find the order of this element 1, we will also get 4. Okay, so order of cyclic group is equal to order of its generator. Okay, so let us move further. So now we have let us go back to the theorem. So we have the criteria of AI is equal to AJ. Okay, so let us consider element G as, okay, so G is a group. Let us consider the algebraic structure as G star. G is a group under operation star. Let us take the elements as G is equal to, so there will be some identity element also here. Okay, identity element a square, a to the power I, a to the power j, like that. Okay, so here we are taking the first case. Okay, in the first case we have, if A has a infinite order, so this means we have studied that order of a cyclic group is equal to order of its generator. So we have taken A as a generator. So if A has a infinite order, then our cyclic group will be of infinite order. Okay, so this we have considered as a order of G is equal to infinity because there are infinite elements. Okay, so we are discussing the first case here. So these two elements are equal. AI is equal to AJ if and only if I is equal to J. Okay, here we have considered A as infinite order. Okay, so by this particular expression, order of cyclic group is equal to order of its generator. So order of generator is infinite. So this means the order of group G is also infinite. Okay, so in the first case, AI is equal to AJ. These two elements are equal if I is equal to J. Okay, so let us take the example as group of integers under addition forms a group. Okay, and we have seen in the previous set of lecture is that the order of the generators are 1 and minus 1. 1 and minus 1 are the generators of this group. Okay, so based on this concept, order of cyclic group is equal to order of generator. So we have the order of this generator is equal to infinite. Order of this generator, that is minus 1, is equal to infinite, because the elements here are elements in this group Z is equal to, this is minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay, so number of repetition, let us find the order of 1. Okay, so how many times we have to operate this? How many times we have to repeat 1? Here the identity element is 0. Identity element of this group is 0. So how many times we have to repeat 1 to get 0? So infinite times we have to repeat. Infinite times repetition on 1 will result into 0. So order of 1 will be infinity. Similarly, order of minus 1. Okay, so how many times we have to repeat minus 1 so as to get the infinite number? So we have, this is minus 1 plus minus 1 minus 1. This is infinite times repetition. Infinite times repetition will result into identity element 0. So this means order of minus 1 is infinity. So order of this cyclic group is equal to order of its generator. So 1 and minus 1 are the generator, and order of these generators is equal to order of this group Z, and order of this group Z is infinite because there are infinite elements in this group Z. Okay, so we have, let us take an example to verify this concept. AI is equal to AJ if and only if I is equal to J. Okay, so we have taken the example of this group of integers. So we have Z as Z is equal to minus, let us take this as minus 3, minus 2, minus 1, 0, 1, 2, 3. Let us take A as A is equal to 2. Okay, let us find 2 to the power 4 and 2 to the power 6. Okay, so here A is equal to 2 and I is equal to, here we have to take A as the generator, na? So the generator here as generators are 1 and minus 1. This is equal to Z. This is generating the whole group. Okay, so let us find 1 to the power 4 and 1 to the power square. Okay, so here we have taken A is equal to 1. Let us relate this with this particular expression. So A is equal to 1, I is equal to 4 and J is equal to 2. Okay, so we have, let us find 1 to the power 4. So this means 4 times operation. This is equal to 1 plus addition modulo 4. This is 1 plus addition modulo 4. 1 plus addition modulo 4. So this is equal to 4 mod 4. This is equal to, remainder is 0. Now 1 square. This is 1 plus addition modulo 4, 1. This is 2 mod 4. This is equal to 2. So 1 to the power 4 is not equal to 1 to the power square because 4 is not equal to 2. Okay, so this expression is valid only if I is equal to J. So here we have taken I to the power 1 to the power 4 and 1 to the power square. Both are not equal because 4 is not equal to 2. Okay, now let us discuss the case 2. If A has a finite order. Okay, so let us discuss the second part of this theorem. So it is given that A has a finite order. Okay, so A is our generator. Okay, and order of A is finite. Okay, so let us consider the algebraic structure as G star. Okay, and G is a cyclic group under operation star. Okay, so based on this statement, order of cyclic group is equal to order of its generator. Okay, so based on this statement, A has a finite order, so the order of generator is finite. This means order of cyclic group is also finite. So order of this cyclic group is equal to order of its generator is equal to finite value. Okay, so we have G as, so G is a group, so there must be an identity element E. Okay, so this means, let us relate this. See, order of G is equal to finite value, and that finite value is n as per the statement. A has a finite order, say n. Okay, so the order of this group G is, will also be n. So order of group G is equal to also n. This means G has n elements. Okay, so G has n elements. So this means we can represent G as, since G is a group, so there must be an identity element, and rest of the elements are a to the power square, a cube, a to the power n minus 1, because we have n elements. Okay, so let us take two elements in this. Let us take ai and aj. Okay, so as per the statement, ai is equal to aj if and only if n, that is order of this cyclic group, divides I minus j. Okay, so ai is equal to aj if n divides I minus j. Okay, so let us relate this with an example. So we have, let us take Z4. It forms a group under addition modulo 4. Okay, so the elements of Z4 are 0, 1, 2 and 3. Okay, so order of Z4 is equal to 4, number of elements. Okay, and the generator of Z4 are, let us find the generators of Z4. So we have the generator of Z4 are 1 and 3. 1 and 3 are the generators. So this is equal to Z4. Okay, because as per the concept, 4 is not prime. 4 is not a prime number. So if A is the generator, then GCD of A comma n. So n is 4 here. A comma 4 is equal to 1. So here A will be 1 and 3. Because GCD of 1 and 4 is 1, and GCD of 3 and 4 is 1. And 0 and 2 will not be the generator, because GCD of 0 and 4 is not 1, and GCD of 2 and 4 is not 1. So A and 3 are 1 and 3 are the generator. Okay, so now let us take an example to relate the expression. So we have the expression as a to the power I is equal to a to the power j if and only if n divides I minus j. Okay, so let us take two numbers here. So 1 to the power 6 and 1 to the power 4. Okay, so 1 to the power 6 will be 1 plus addition modulo 4, 1 plus addition modulo 4, 1 plus addition modulo 4, 1 plus addition modulo 4 plus 4. So this is equal to 6 mod 4, I to the power 1 to the power 6. This is equal to 2. 2 is the remainder. Similarly, 1 to the power 4 is equal to 1 plus addition modulo 4. This is equal to 4 mod 4. This is equal to 0, because 0 is the remainder. So 1 to the power 6 is not equal to 1 to the power 4, because, and here I to the 1 to the power 6 and 1 to the power 4. So based on the expression, this one, we have a is equal to 1, I is equal to 6 and j is equal to 4. So I minus j is equal to 6 minus 4 is 2. Okay, so 1 to the power 6 is not equal to 1 to the power 4, because here n is equal to 4. So 4 does not divides I minus j. 4 does not divide I minus j is 2. Okay, so based on the expression, a to the power I is not equal to a to the power j, because n does not divide I minus j here. Okay, so ai is not equal to 8j, because n does not divide I minus j. Okay, so if A is of finite order, this means generator has a finite order, then ai is equal to aj if and only if n divides I minus j. Okay, so this we have shown with this example. So 1 to the power 6 is equal to 2 and 1 to the power 4 is equal to 0. Okay, so here n is equal to order of the generator, that is based on this expression it is also equal to order of the generator. So order of generator is 4. Okay, so here n is not dividing I minus j, so n I minus j is 2, so 4 is not dividing 2. Okay, so now let us proceed further. So we have the corollary here, as corollary is equal to order of element is equal to order of group generated by that element. Okay, so let us discuss this with an example. Okay, so we have the corollary as order of element is equal to order of group generated by that element. Okay, let us take an example. So we have Z4 is equal to, this is 0, 1, 2 and 3. Okay, and Z4 forms a group. Z4 forms a group under addition modulo 4. Okay, so let us take the, and it has, let us take the element 2. Okay, so the order of element 2, find the order of element 2. Okay, so let us apply the operation addition modulo 4. So we have one time operation, this is 2 mod 4, this is equal to 2, 2 to the power square, this is 2 plus addition modulo 4, this is 4 mod 4, this is 0, 2 to the power cube, this is 2 plus 4 and this is 2 square, so this is 2 plus addition modulo 4, 0, 2 mod 4 is equal to 2, 2 to the power 4, this is 2 plus 4, this is 2 to the power cube, so 2 plus 4 and this is 2, 4 mod 4, this is 0, so elements are getting repeated. Okay, so order of element 2 is equal to 0, because 2 to the power square is also 0 and 2 to the power 4 is also 0, so we have to take the smallest natural number, so the order of 2 is equal to 0. Okay, and the group generated by 2 is, so here the group generated, 2 is generating a group and the elements are 0 and 2. Okay, so 2 is generating 2 elements, that is 0 and 2. So the order of group generated by 2 will be number of elements. So number of elements in this particular set is 2. So this means order of element 2 is equal to order of group generated by 2. Okay, so this is basically this particular expression. So let us verify this with element 3. Let us find the order of element 3. So order of element 3, so we have order of 3 is equal to order of 3. Let us find this. So we have find the order of element 2 as 2. Let us find the order of, this is 2. Let us find the order of element 3. Okay, what will be the order? So we have, let us apply this operation. So we have one time operation, this is equal to 3 mod 4, this is equal to 3. We have 3 square, this is equal to 3 plus 4 mod 3, this is equal to 6 mod 4, this is equal to 2 is the remainder, 3 to the power cube, so this is equal to 3 plus addition modulo 4 and this is 3 square, this means 3 plus 4, this is 2, 5 mod 4, so this is equal to 1, and we have 3 to the power 4, so this is equal to 3 plus addition modulo 4 and 3 to the power cube, so this is equal to 3 plus 4 and this is 1, 4 mod 4, the remainder is 0. So 3 to the power 4 is equal to 0. This means order of element 3 is equal to 0. So order of element 3 is equal to 0. And order of 2 is equal to, order of 3 to the power 4 is equal to 0. This means order of element 3 is equal to 4. Okay, this is equal to 4. So the group that is being generated by 3 is, it is generating the elements as 0, 1, 2, 3 and 0, 0, 1, 2, 3. So this is generating 0, this is 0, now we have 1, now we have 2 and we have 3. So the order of group generated by 3 is equal to 4. So we have order of element 3 is order of element 3 is 4, and this is equal to order of group generated by 3 is equal to 4. This is verified. So this is equal to order of group generated by 3, and this is equal to order of group generated by 2. Okay, so we have here, let us write down here. So 2 is generating a group, this means it has two elements 0 and 2, and 3 is generating a group, and this is equal to Z4. Okay, so we have the order of element is equal to order of group generated by that element. Okay, so here let us let us understand that in Z4 we have the generator as 1 and 3. Okay, so 1 and 3 is generating a complete cyclic subgroup, that is Z4, but 2 is not generating the complete group, rather it is generating a cyclic subgroup of Z4. So 2 is generating a group that is 0 and 2, and 0 is generating a singleton 0 element. So these are the cyclic subgroup. These are not the complete subgroup. This is not the complete group Z4. Rather, 2 and 0 are generating the cyclic subgroup of Z4. These are cyclic subgroups. Okay, so this expression is valid in the case of generator as well as the elements that are not generating the complete group. Okay. So 0 and 2 are not generating the complete group. Okay, so this expression is valid for both the cases. In the case of generator as well as in the case of elements that are not generating the whole group. Okay, so here 0 and 2 are generating the cyclic subgroups of Z4. It is not generating the complete group. Okay, now let us discuss this one. Corollary 2, a to the power k is equal to e implies that a mod divides to k. Okay, okay, so let us discuss the corollary 2. So we have a to the power k is equal to e implies that order of the element divides k. Okay, so let G be a group and let A be an element of order n. Okay, in G, if a to the power k is equal to e, then n divides k. Okay, so let us discuss this. So we have, let G be a group. So G is a group under operation star. Okay, and A be an element of order n. So A belongs to G, and order of A is equal to n. If a to the power k is also e, then n divides k. Okay, so based on the definition of order of an element, we have if a to the power n is equal to e first, then n is order of element a if n is the smallest natural number. Okay, so there are 2 points here. If a to the power n is e, and secondly n must be the smallest natural number. Suppose we have a to the power square, a to the power 2 is equal to e, and a to the power 4 is also e. Then we have the smallest is 2. So the order of element a will be 2. This is the concept here. Okay, so let us take the example. Let us take the example of addition modulo, Z4 is a group under addition modulo 4. Okay, so the elements in Z4 are, this is 0, 1, 2 and 3. Let us find the order of element 2. Okay, so we have 2 to the power 1. Let us apply the operation. So this is 2 mod 4. This is equal to 2. 2 square, this is 2 plus 4, this is 2. This is 4 mod 4, this is 0. 2 to the power cube, this is equal to 2 plus 4, this is 2 square. This is 2 plus 0, that is 2 mod 4, this is 2. 2 to the power 4 is equal to 2 plus 4, this is 2 cube. This is 2 plus 4 and this is 2. 4 mod 4, this is 0. So elements are getting repeated. Okay, so based on the concept of order of the element, we have 2 square is equal to 0 and 2 to the power 4 is also 0. So we have to take the smallest natural number. So 2 square is equal to 0 and this is equal to 2 to the power 4. So both are giving the identity element. So we have to take the smallest natural number. So the order of 2 is equal to, order of element 2 is equal to 2. Okay, and we have 2 to the power 4 is also identity. This means 2 divides this 2 divides 4. Okay, so this means we can say that order of element 2 divides 4. Let us take this as k. Let us take 4 as k. So 2 divides 4. This means order of element divides k. Okay, so if a to the power k is identity and we have the order of element a as n, order of element a as n. So order of, here we can write this order of element divides k. This means n is the order of element a. So this means order of element a divides k. This is basically the statement wants to tell you. A to the power k is equal to e implies that a mod is order of element. Okay, so in this particular example we have a to the power, we have taken a as 2. So 2 to the power 4 is equal to identity, is equal to 0, and 2 to the power square is also identity. Okay, so order of element 2 is equal to 2 because 2 is the smallest of 2 and 4. So smallest of 2 and 4 is 2. So order of element 2 is 2. So order of element 2 is dividing this 4, and we have taken k as 4. As simple as that. Okay, so we will discuss further in next particular lecture. Thank you.